Okay, here we go with part two. We've got an example here. We're going to see a couple of types of questions. This one is generating your own model, that second type that we said, generating our own model and using in a measurement situation. So this idea, farmer wants the fence in 4 pens as shown, like this. She has 200 meters of fence, so all these lines add up to 200 meters. What dimensions would give a total area of 800? Okay, well, area is not so bad, right? Area is just length times width, but the question is, what's the length and what's the width? Well, we're going to come up with expressions, right? Because it's not just this and this. This and this have to, all this stuff has to add up to 200 meters of fence. So what am I going to do? I'm going to choose a value x and write it on there. I'm going to say, well, I'm going to let that distance be x. Okay? And in fact, I'm going to call that the width rather, of this farmer's field, the pens. I'm going to call that x. Okay? And so what's the length going to be then? Well, it's got to be how much ever is left over from the 200 meters of fence, right? So I'm going to do a little rough work here. So 200 meters, but I've used 5 x's to do the vertical parts here, right? So that's how much fence is left after I take off all the widths. Notice, but I have to put fence along both the top and bottom here. So how much is left for one length is I divide that by 2, right? Part up here and part up there, and all of that stuff will add up to the 200 meters of fence. And notice I'm going to just divide that 2 into there. That's 100 minus 2.5x. And that's going to be an expression for the length. And so the area as a function, a model, did you see that mistake I made? 100 minus 2.5x. So I got to fix that up. 100 minus 2.5x, and then the width is just x. So if I wanted to simplify that a little bit, my model is 100x minus 2.5x squared. Quadratic. It's quadratic. And I want to know when this area is equal to 800. So I want the area to be equal to 800. There's my model. 800 equals 100x minus 2.5x squared. I've got to put everything on one side, and I'm going to hope that this thing will factor once I clean it up a little bit. And if it doesn't, it's a quadratic, right? I can use the quadratic equation. I'm going to divide each part by 2.5 just to make it an easier equation. What I did there was I divided by 2.5. And this is getting pretty cramped. This doesn't factor. So I could try and find numbers that multiply to get to 320 and add to get to negative 40, but it doesn't work. So what am I going to do? I'm going to use the quadratic formula. I have x equals negative b plus or minus the square root of blah, 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 blah. Off we go. Right? This is getting to be old news now. You almost cheer for it to be factorable because this is a pain. Big pain. And I should get 2 solutions, which that kind of makes sense. Maybe it's, I could make it x one dimension this way and it'll be longer or wider or whatever, but let's see. So I got x equals, after I go through all this, I get x is equal to, I'm going to put dot, dot, dot there. You can fill in the details with your calculator. 11.1, or x equals 28.9. Now one of the questions is are both these solutions okay? Both of them are positive. Is that okay to be 11.1 meters? is that okay for that to be 28.9 meters? Well, it should be. What would be the problem? Well, um, notice I don't want to use up too much fence. If I use up too much fence for x, then the length would be negative. And I don't want that. Well, what would be the rule? Notice as long as the length is positive, I'll be okay. Well, what value of x makes the length positive? Notice then I'm thinking about 100 minus 2.5x is greater than 0, greater than or equal to 0. And just by inspection here, I see x has got to be less than 40. So if I put in 50 there, I'd get the length being negative. So there's the rule. And notice both of these are solutions. So he could, I don't know how I'm going to fit this sentence in here. The farmer could make the pens 11.1 meters long or 28.9 meters long. And then I suppose we should figure out what the width would be, right? What would the width be? Well, all I would have to do is substitute x back in there, and I can do that. Where's my calculator? Substitute that back in there. I got 200. Clear. 100 minus 2.5 times x, which is 11.1, 72.3 meters wide. And notice maybe I should have these words switched here, but you get the idea. This is 11.1 and this is 70.6, or this other value might work as well. So what's that? 100 subtract 2.5 times 28.5, 9, that's supposed to be 9, equals, oh, something weird happened there, 100 minus 2.5 times 28.9, 27.5. So notice that this one is kind of short pens and long this way, and this one is long pens and short this way. And that's to get a total area of 800. Well, what about the maximum area? Well, we don't know how to do that. So as soon as we find the maximum, we're going to turn to the TI-83, right? Turn to the TI-83, and I want to find the maximum of that function. Well, I'm going to put that into my calculator, get the graphing calculator going. Fire it up. There it is, actually. Notice that there's my area formula. The area formula goes in there. And my window settings, notice I set them up for you, but it makes sense. I don't want x to be any more than 40, so I set my maximum to be 40. And notice my area was 800 up here, so I figured maybe I can get a little bit more than 800. I went up to 1,000. That's where I got my window settings. Now if I press graph, there it is. And I can see the maximums right there, but I'm going to use the second trace maximum. Find the left bound, the right bound. There's the little spider in the middle, and I get a maximum at 19.9. That's 20, right? That's just rounding error. So the max, this point here, is 20 and 1,000. A max area of 1,000 meters squared occurs if x is 20 meters, so that's 20, and then I can figure out what the length was. And the length is 100 minus 2.5 times that. That's 50, isn't it? Nice. Okay, well, I got another example. Another one of these measurement ones. Piece of cardboard cut is like this to make a box with a top. So the idea is this folds over and it's kind of like a pizza box. To do this, a small square is cut. Those gray pieces are cut out from the corners as shown. Write a function for the volume. Well, the volume of a box is good old length times width times height, but here, let's come up with formulas for the length, the width, and the height. The length, I'll call this side. Well, notice the length of the box, that part's going to be folded over. So how much is this? This is 25, and this is 25. So that piece right there is the length. That's the length. The length is going to be 25 minus x. The width. Well, the width is this part right there. That's the width. The width is going to be the 35 centimeters, not minus x, but minus 2x. Right? Minus 2x because there's one there and there's one there. 35 minus 2x. Well, what's the height? Notice if I fold these little flaps up, that's going to be the height of the pizza box, right? The height is just x. And so if I wanted to write a formula, a model for the volume, v at x, that's supposed to be v at x there, the length times the width times the height. Notice that I could switch the length and the width or even the height, and I'm still going to get the same model. I'm not going to expand that. I want to see what else is going on before I try and do anything more difficult than this. When will the volume be 2.5 liters? So 2.5 liters is the volume. That's the volume. I want to know what value of x will give me a volume of 2.5 liters. Well, 2.5 liters, remember, 2,500 milliliters is 2,500 centimeters cubed. So I want to know when this bad boy is equal to that. And this sounds like a lot of work, and who knows if this will work out nice. Let's go right to the TI-83 right away. Why not? So how do I solve these questions? Well, we've done this quite a few times, right? I'm going to put in the left-hand side into y1. I'm just typing straight over all this other business. Times x. And the right-hand side, I'm going to find out when this is 2,500. Now, I'd love to just press graph, but I've got the window settings from the old one. Let's think about this. What would be decent window settings here? Well, what's a decent value of x? Notice that if x was any more than 25, I'd be chopping off this side, and there would be no length there. So I know that x has got to be less than or equal to 25. But look at this side. What's the restriction here? This has got to be positive. The width has to be positive. So in fact, if I cut off half of this, that would wipe out this entire flap here, and that gives me a restriction. X has got to be less than 35 divided by 2. That's 17.5. So the most that x can go up to is 17.5, it looks like. I'm going to give it a little wiggle room and say that x can go up to 20, say. Okay? Just for funsies. And then the scale, maybe I'll go up by 5s instead of 10s. Now, as far as the volume's concerned, I know the output of this has got to go up to at least 2,500. Let's go a little more than that. Let's say 3,000. I'm going to go up by, maybe go up by 500s here, just so we can get up to 3,000s. And I want to see what this looks like. I want to see where they cross. It's kind of a strange look, but there's the 2,500, and there's the two spots where it's equal, right? So if I'm going to solve this, I can use my intersect feature, intersect of this function and this function, and I should draw a graph so I can, I'm going to copy this actually, aren't I? I'm going to cheat. You guys will have to copy it. That goes down there. And that first value, and then I'm going to write the second value. So looks like the cut that gives me a volume of 2.5 liters is 8.6 centimeters, so or 8.7 centimeters. So I could make that square 8.7 centimeters. That's one of the solutions, but I'm going to find this other one now. Calc, no, second calc, intersect, first curve, second curve, and then I'm going to go over to the guess here. 5. That point is x equals 5. So then from this, the cut could be x equals 5 centimeters or x equals 8.7 centimeters about. And that's going to give me a volume of the 2.5 liters, the 2,500 centimeters cubed. What I want to mention here, though, is this model with x equals 5 as a solution, there must have been some way we could have got that. That's an exact answer. I should have been able to get that using the factor theorem or factoring or something like that, and I could have. And I'm you know, you're not going to copy all this out, but here's the solution. You know, I wanted to know when this was 2,500. Then I'm expanding all that business, move the 2,500 there so I have a 0 on this side, and then I can start factoring it. I know that x equals 5 is a factor, and so I can use long division like we've done a million times in this chapter and last, and so then I can factor it, and then I end up with a factor, a quadratic factor that doesn't factor, and then I can find these other two solutions using the quadratic formula. And there's that other one we use on the calculator. What's weird is that one right there. Where did that one come from? X is 28.8. Well, if I think about the model, this is a cubic model, right? It's going to come back up at some point, right? It's going to come back up over at 28.8. Why did that not show up? Well, it showed up because I didn't go out that far. If I went out to 30 and press graph, went down like this, and that's 28 right there. But we also said that wouldn't make sense to make a cut that's 28 centimeters, because that means I'd be hacking off the whole side of the piece of cardboard. So we're not allowing that solution. That 28.8 doesn't make any sense, so it's okay that we skipped it. Okay, that 28.8 was inadmissible. That's the fancy math term for not allowed, since x is less than 17.5. Okay, big lesson today. Have fun with the models and the questions. Probably not many questions because they are so huge. Have fun with that. Say two. That's all.